Looks like we got about 17 of us on the call right now. So I think we should just start in, and I'm sure there's probably will be some other people that come on as we're talking. But I'm Kirsten Engel from the law school, and together with Robert Glennon, also on the call here, we're hosting our monthly Environmental Breakfast Club. This is our last one for the fall, but we'll be starting up again, I believe. Robert, are we starting in January or February?
February. We tried it in January and no one came.
Okay.
So we'll, an intercession, getting people after, and same at the end of the year. It's
Right.
a tough sell.
Right. Okay. Okay. But today we've got a really interesting presentation. Looks like with Professor Jesicca Barnes from the College of Science, the Lunar and Planetary Laboratory. Just got a recent NASA grant about collecting samples on the moon, and understand that she's already, she's been spending more of her time online than in person, which is really too bad, but we're looking forward to the time that we can greet you in person. But for now, so nice to have you. And anything you want to say to introduce yourself before you get started is just great.
Perfect, thank you. So yeah, my name's, you can call me Jess, that's fine. So I got to the U of A about a year ago. Prior to that, I did my PhD in the UK. I'm a British citizen. I did my PhD in the UK at the Open University. I did a short postdoc there before moving to NASA's Johnson Space Center in Houston, where I did a postdoc for about 3 years, a postdoc fellow, before coming to the U of A. So at the moment, I wear 2 hats. My main passion is looking at moon rocks and trying to understand water, which is what I'm going to talk today about. And then the other hat I've taken on recently is getting prepared for analyzing material returned by the OSIRIS mission. And so maybe in the future, I can come and talk to you about what we're doing with regard to that. So yeah, that's a bit about me. And so I'll just dive right in. Today, I'm going to be focused on kind of giving you a brief on what my main research focus is, so water inside the moon, kind of tell you how we go about looking at lunar samples, why we care about lunar samples and water inside the moon, and then give you some future perspectives, which include talking about NASA's initiative to look at what we're calling new lunar samples, but they were actually collected in the Apollo era. Okay, and so a lot of my talk is going to be on water. I'll be talking a lot about volatile elements as well. And so volatiles are really important, and magmatic volatiles in particular, the elements and molecules that you see here, as they really control physical processes that control thermal stabilities of minerals and melts. They control the way magmas move through the crust up to the surface. They control magmatic eruptions and volcanic eruptions. And volatiles also are really important in transporting elements through the crust, in particular, economically important metals in, for example, rare earth element deposits. And so by studying samples and measuring volatiles in those samples, we can better understand not only how Earth formed and evolved, but we have samples from extraterrestrial bodies like the moon and Mars and small bodies. We can understand how those planets formed and evolved. And by a lot of the work that I do involves looking at isotope ratios. And so we can use the isotope ratios of some volatiles to give us an understanding of where in the solar system, in this case, water originated. And so how we do that, we can use water, so the isotopes of hydrogen, so the isotopes of nitrogen, to basically fingerprint different sources of volatiles in the solar system. And so I'll walk you through what plot is. I'll be talking a lot about delta D, or hydrogen isotopic composition. And what that is it's the deuterium to hydrogen ratio of a sample over the deuterium to hydrogen ratio of a standard, given in a per mil notation. So -1 times 1,000. This is the notation that we use, this symbol, and the values in per 1,000. The standard that we can refer is Vienna standard mean ocean water, which by convention has a delta value of 0 per mil. And so when we're talking about delta D, that's fine. For nitrogen, it's the same. We would have the heavier isotope, the nitrogen 15 over the nitrogen 14 in a sample compared to a standard. And so when we plot or make a plot to one of these discrimination fingerprinting diagrams, we have the delta D values along one axis, the corresponding deuterium to hydrogen ratio is on the other axis. And then on the vertical axes, we have the nitrogen isotopic composition and the delta value that is corresponding to those ratios of the sample. And so the take-home message from this plot, this is like a summary diagram of lots of different bodies across the solar system and what we know about them. And you can see there's a large spread in both delta D value and also in delta nitrogen 15 when we compare the solar photosphere with rocks from Mars, rocks from all these little symbols in the middle are corresponding to different asteroid parent bodies. So the Crite parent body, or if you've ever heard of the asteroid 4 Vesta, we think that those meteorites come from that body. The squares are all the carbonaceous chondrite meteorites that we have. And then Earth is represented by the triangles. But then over here, we have a really large spread in the isotopic compositions of comets. And so what we want to do with regard to the moon and with other planetary bodies is we want to compare the values that we measure in the laboratory with these different sources of water. So whether we're looking at a solar source, whether we're looking at a cometary source, or whether we're looking at something from the carbonaceous chondrite realm. And so when we go to the moon or we go to Earth or those other planetary bodies I mentioned, having knowledge of the volatile inventory of the terrestrial planets is really key to unraveling what objects were delivering water to the inner solar system. When we think about how the solar system formed and evolved, we think the inner solar system, so everything inward of Jupiter, would have been very dry, very water poor. Whereas in the outer solar system, beyond the orbit of Jupiter, ice would have been stable. It would have accreted into, accreted with dust, and then formed larger and larger bodies into what we think are most of the carbonaceous chondrites and comets. And so if we want to explain how Earth got to be water rich, or we want to explain water and any of these other inner terrestrial planetary bodies, we need to understand how they got their water. That helps us to understand the flux of materials coming into the inner solar system. It helps us understand how those bodies formed and evolved. And because volatiles play such an important role in the stability of minerals and melts, it actually changes our perception of how a body can magmatically evolve over time if we include water versus not including it. So ultimately, any question that looks at water is intimately tied to understanding the origin of life on Earth, because as we know it, life requires water to survive. And so the question you're probably asking yourself, why do we care about the moon? And a lot of people think, been there, done that, but the moon is really important to understanding the entire solar system. It's the most accessible body that we have outside Earth. It's Earth's companion. It is a treasure trove of the entirety of solar system history since the moon formed about 4.5 billion years ago. And if we want to really understand how Earth formed, evolved, and came to be this, life-giving planet, we know it, we need to understand Earth's earliest history. The problem with Earth is we have tectonics, and so that earliest history has been erased, but it is recorded on the moon. And so the moon is a touchstone to understanding the entire system. And so today what we're going to focus on is understanding, well, we've heard that volatiles are really important. We've heard that the Earth's earliest history has been erased. So is there any water in the moon? What was the role of hydrogen during magmatism and volcanic eruption? And where did the moon get its water, and does that link to how Earth got its water?
Jessica, open to a few clarifying questions as we go along.
Oh, yes, sorry.
Oh, great.
So, yeah, go ahead.
I don't know if anyone else has any, but you just talked about, you said there's tonics on Earth that has sort of erased Earth's history on this. And that's not a term that I'm used to, and I'm wondering if you can explain it a little bit more.
Oh, I'm sorry. It's either my accent or the internet cut me off. So I was talking about plate tectonics.
Plate tectonics.
Plate tectonics, yes. So the action of creating new crust on Earth and subduction has largely, erased that earliest record that we have on Earth.
Okay, wonderful.
Please keep interrupting me if something's not clear.
Okay.
Okay, no problem. And so the last point is, what information can be gained to understand the moon and the water on the moon from studies of new lunar samples. And so I'm sure you're all aware, but in order to study the moon, we can do that in one of two ways. We can or three ways really. We can either go to the moon and study it in situ, like a field geologist, or we can remotely observe the moon, or we can look at lunar samples. And really, lunar samples are the key to understanding lunar science. It's how we ground truth, the results we get from orbit, and also how we compare different places on the moon that we have explored to places we have not. We have 3 different collections of samples right now. That's about to change. If I have time, I'll get on in a second. We have Apollo samples, and that's the focus slide, but we also have Luna samples that came back between 1970 and 1976 from the Luna Soviet Union missions. We also have lunar meteorites. So these are rocks that are kicked off the surface of the moon and they enter Earth orbit. They travel through the atmosphere and land on Earth. And then we go and get them either as a find in a hot desert, or we witness them falling and then we can go and collect them. But the main way we study lunar samples is the huge Apollo sample collection that was brought between 1969 and 1972. There were 6 sample sites, so 6 landed missions to the moon. Each of those collected Apollo samples. And we had about 382 kilograms of material that was returned. And in total, over 2,000 individual samples were collected. And so what you see on the screen represents the variety of materials that were brought back. Anything from volcanic materials, like you see up here, to what we call plutonic rocks, and I'll explain that a bit later, rocks of the crust. If you look up at the moon, there are light and dark areas. So the dark areas are the volcanic materials, the lighter areas are the crust. And then everything in between. We have mixtures in the form of soils. We have core tubes. So cores literally cored through the surface into the stratigraphy below. And we have breccias. So those are materials formed by impact events that essentially mix up everything that was on the surface and basically lithify it into a rock. And really, these samples have been curated in such a way that they remain pristine to this day, and they provide geologic context that we wouldn't get if we went and robotically sampled the surface. And that's because we sent humans with these Apollo missions. These samples have been really critical for understanding how the moon, how the moon formed. And before the Apollo missions, there were several hypotheses floating around for how the moon may have come to be. But it was really the Apollo samples that grounded our understanding and made us realize that the Earth-Moon system is maybe more intimately linked than we thought. And so the prevailing hypothesis for how the moon formed is that we started off with a proto-Earth, and about 4.5 billion years ago, Earth was impacted by a relatively large body, the size of Mars. And that impact caused a lot of material from the proto-Earth mantle to be flung out into Earth orbit and then coalesce, as you see here, coalesce into a moon on the, in Earth orbit. And so we think from numerical simulations like this one, that the large majority of the moon formed from the Earth's mantle and not from the impactor that impacted the proto-Earth. And so you can tell just from this slide that the Earth and moon are genetically related. They're intimately linked. But what happened after that? So the key to understanding lunar rocks is really to understanding how those rocks came to be and how their sources were formed. And so if we imagine shortly after the moon accreted, we have a body that looked something like this. This is an artist's rendition I really like. That body would have been really hot and potentially fully molten. And so as you cool that kind of body, you're going to start forming crystals. So this is just a pie of the moon as it's cooling. And the first minerals to crystallize would have been rich in magnesium and iron, forming minerals like olivine and pyroxene. And those minerals would have been heavier, more dense than the remaining liquid, and would have sunk to the bottom of the magma ocean, this molten body we're going to call the magma ocean. No. And over time, the mantle would have grown upwards because you have continual sinking of these minerals into the bottom of the magma ocean. At about 70% crystallization of body of magma, things change and plagioclase becomes stable. And plagioclase is a calcium aluminium bearing mineral that's less dense than the liquid we think it would have been in equilibrium with. And so plagioclase being less dense is not going to sink to the bottom of the magma ocean. Instead, it's going to float to the surface. And so that's depicted here, that the crust starts to form, this plagioclase crust starts to form, and instead of growing upwards, the crust is going to start growing downwards. So we end up with kind of a sandwich. The mantle is growing up, the crust is growing down. And so when we get to the very, very final stages of crystallization of this magma ocean, we're left with a melt or a magma that's really enriched in all the elements that didn't want to go into the minerals that formed the mantle or the minerals that form the crust. And so we call this kind of residual pink horizon that you see here, we call that creep. And that's because it's enriched in potassium, rare earth elements, and phosphorus, incompatible elements. Now, as we've crystallized the mantle, we've gone from a magnesium-rich scenario to a very iron and titanium-rich scenario overlying it. And that's the density is not stable. You've got something much more dense and much heavier on top of something that's relatively low density. And so we think after this point in time, the magma ocean would have reorganized itself, hybridized, and you would have had material from higher depths, so up here, falling into the deeper magma ocean. So more dense material would mix in through the magma ocean. And subsequent melting of this heterogeneous cumulate pile gave rise to the magmatic activity we now see at the surface and have collected with the Apollo missions. So the crust, as we see in the meteorite record and also in the Apollo samples, the crust is very old. So 4.5 billion years to about 3.9 billion years old are the record of rocks collected from the Apollo missions on the surface. And then the Mare basalt, so those darker regions that you can see clearly on the, if you look up at the moon on any given night here in Arizona, you can clearly see the darker regions. These are the volcanic regions, the Maria, and they really extend anywhere from about 4.3 billion years to about 3 billion years old is what we record in the rock record. But sensing observations suggest that volcanic activity even extended much later than that, to about 100 million years ago. And we have a variety of different chemical types of basalts or volcanic rocks. And so going back to kind of our theme of this talk, we want to understand, is there water in the moon? And this seems like a kind of a silly question to ask now, given that we're in 2020. But 10 years ago, this wasn't a silly question. And that's because during the Apollo era, when they studied the samples brought back, there was very little evidence of indigenous or original lunar water in those samples. Any water that was detected couldn't really be disentangled from terrestrial contamination. The mineralogy of lunar samples is very different in some ways to what we see on Earth. On Earth, we have lots of water-bearing minerals that contain weight percent levels of water, so lots of water. On the moon, it wasn't that obvious what the water-bearing minerals would be. And Also astronaut observations. You know, the astronauts went to the surface. There's no evidence for liquid water on the surface of the moon. No channels carved by running water, nothing like that. And so the Apollo era really dubbed the moon as a bone dry body with less than a part per billion water in its entirety. But that changed. Towards the late 1990s and the mid 2000s, we began sending spacecraft to the moon to see if we could find water ice on the surface in areas of the moon, in these craters that you see, these like little pots on the surface, to see if we could find water ice in those craters. And remote sensing this is a spectroscopy map showing you in blue areas where we find water ice on the surface. You can see it's concentrated at the polar regions of the moon, but actually we find water ice all over the surface. And so this remote sensing really hit its pinnacle in about 2008. And that's when we find out, okay, actually there's water on the surface of the moon. And that really prompted people to start looking at samples in more detail, which I'll talk about in a second. Something that we struggle with as a community is that even though since about 2008 all the way through to today, we've been doing remote sensing, remote observation of the moon, there's huge variation in the abundance and distribution of water at the lunar surface, and also the speciation. So whether it's hydrogen, hydroxyl, or water mixed in with the soil, we have huge variations. And so we're not quite sure what the abundance of water is on the moon at poles. And there's this theory that actually water ice can be a really important resource going forward for future exploration of the solar system. I'm not going to talk too much more about that though. So we see water on the surface and the exterior. What about in the interior? And this was really what I focused on for my PhD and have been doing pretty much ever since. And so around the same time that we detected water definitively at the surface of the moon, people decided to go back and look at the lunar samples using brand new analytical techniques that weren't available in the Apollo era. And so what you see here is a picture from Apollo 17 taken by astronaut Jack Schmitt, who was the only geologist to go to the moon. And you can see this orangey brown deposit on the lunar surface. That deposit is chock-a-block full of these orange glasses. These are volcanic glass beads that we think were erupted from a vent on the moon in a volcanic vent, similar to the kinds of eruptions that we would see on Hawaii. Except unlike on Earth, on the moon, when a volcano's erupting or a vent is erupting lava, it doesn't, because you're erupting it into the vacuum of space, it instantly freezes in the vacuum and then falls to Earth, or falls to the moon, sorry, as these spherical glass beads. So anyways, so using the detection of lunar surface water as a driving force and using new state-of-the-art techniques applied to those Apollo samples collected 40 years prior, and using instruments like this one, we were able to discover water inside lunar samples definitively for the first time. Even if it's in small quantities, it was definitely lunar water. And so the first paper and first study to do this was a group at Brown and Carnegie, and they detected water in lunar glass beads in 2008. And this just was not possible in the Apollo. We did not have the capabilities to understand we didn't have the technological capabilities. We didn't have the sample preparation technique. We didn't have the ability to discern what's terrestrial contamination from what's indigenous and lunar. And so what I've been doing the past few years is not looking at those volcanic glasses, but instead looking at the rocks that we have back from the moon. And although I said before, people hadn't really found a water-rich mineral, there is a mineral in almost all lunar samples. that does contain a hydrogen species. It contains hydroxyl, and that's the mineral apatite with this chemical formula. It's a calcium phosphate mineral that incorporates volatile elements like hydroxyl, chlorine, and fluorine into its crystal structure. And the majority of lunar apatite is rich in this fluorine end member, fluorapatite, but it does contain variable amounts of the other two components. And in case you're wondering about apatite, we're all familiar with it, whether you know it or not. It's a mineral that comprises most of your bones and teeth. So how we do this in practice is we take rocks and we make tiny thin sections, about 30 micrometers thick, and we identify apatite in those samples, and then we measure using an electron microprobe the composition of apatite. And so we usually plot the mineral chemistry on a diagram like this, where we're just focusing on the constituents of this crystallographic site in the apatite. You're probably asking why apatite? Well, it contains these essential structural constituents, and so any hydrogen-bearing species or volatiles that we find in apatite, we know it's likely to have been derived either from the melt from which that crystal grew, or by other processes involving fluids or vapors or other melts. So it can give us an indication of the melt volatile content. So we can understand, we as a rock crystallizes, we form crystals. But what we want to know is what the original melt contained. And so perhaps we use apatite to do that. It's present in not just the majority of lunar samples, but in the majority of planetary materials, so asteroidal samples, Martian samples. And so we can use that as a tool to interrogate volatiles and water in different planetary bodies. And it can preserve volatiles through processes in which volatiles are lost, and can give us an idea about those processes that are operating or operated in the past. And so I wanted to show you a little bit how we actually do this in practice. So we take these thin sections of the rocks and we use a scanning electron microscope, and we have several of these in the Kuiper imaging facility in LPL. And so what we do is we use the scanning electron microscope to get these really nice X-ray maps of to tell us about the mineralogy that is in the samples. And so you can see that this is a combination of lots of different maps as indicated by the colored boxes. And so in this case, apatite sticks out because we've color coded the calcium map as yellow. And so you can see that we can identify these yellow apatite crystals. And then we can go back after we've done our X-ray mapping, we can go back and then look at, take really nice images. This is a backscattered electron image of the sample. And what you're seeing in the different gray colors are basically minerals with higher atomic numbers versus minerals with lower atomic numbers.
So Jesicca, I have a question. So is this, are you saying that as a result of breaking down and seeing this, that water had been in, water must have been there in order for you to see the chemical composition of this apatite now, or is water actually in there somewhere?
It's actually in the crystal structure. So it's still there. It was a long time ago, and I'll talk about that in a second, and it's still there today. And so what we're measuring is the water that's locked into that crystal and has been there for potentially billions of years. A lot of the samples that we look at are on the order of about 3 billion years old to 4 billion years old. So really ancient water.
Okay, and so when you say volatiles, are volatiles the apatite, or volatiles is a larger, I'm not sure I entirely understand what is encompassed within volatiles.
Oh, okay. So when I talk about volatiles, I'm talking about those elements that have really low boiling points. So if you were to start heating up a liquid, they would be the things that start, the elements and species that start leaving at relatively low temperatures. Things like water, hydrogen, chlorine, carbon, those kind of things. Does that answer your question?
Yes, actually, we have a follow-up question. Scott Zalesko is here with me. And actually, Carl, I think you need to mute. Hi, Carl. Wait, and your question, Scott?
Oh yeah, I was just wondering, so is this what you're talking about now, this water lock in the Apatite for billions of years? Is this the discovery that got all the headlines recently or something else?
So you mean very recently, as in a couple of weeks ago?
Yes, yes, exactly.
So that discovery was using a telescope to the surface water. So what I'm talking about here is we've discovered water on the surface, but when we look at the samples, we're really looking at water that was locked into the moon at a very early point in time. So very shortly after the moon formed. So that's now recorded in the rock record for us. So something that I'll get onto in a minute is we have a lot of open questions about how we relate magmatic water, so water locked inside the moon, what we observe remotely or from the SOFIA spacecraft project that you're talking about, where they actually observed water at the surface.
Are you going to connect that to this work? Or are those
Eventually, yes. And so once we identify apatite, we can then use what's called a nanoscale secondary ion mass spectrometer to not only measure the amount of water that's in the crystal, but also its isotopic composition, which dates back to the fingerprinting I was talking about earlier. And so going back to hydrogen isotope systematics, we can, this is the same formula I showed you before, measuring the deuterium to hydrogen ratio of the sample. So deuterium and hydrogen are two isotopes of hydrogen, with deuterium having one more neutron than hydrogen. And so when we measure the hydrogen isotope composition of the sample, compare it to the standard, we get the delta D value. At the same time, we're measuring the water content of these minerals. And so water content is parts per million on the x-axis, and delta D versus the standard is on the y-axis. 0 is where our standard is, because by convention, it's the value of 0. And when we go to values more positive, we're talking about having more deuterium. When we go to negative values, we have more hydrogen. Okay, and so I'm going to skip through some of these because I'm conscious I'm short of time. When we've looked at the volcanic rocks, we understand that there, if I just come to this plot, there's a huge range in the isotopic composition and also the water content that we measure in volcanic samples. And these different symbols represent different geochemical compositions of volcanic rocks. It's important to know that there's a spread, but we think we can match spread or explain that spread by a mixture of different magmatic processes. The most prevalent being the loss of water as volcanoes are erupting lavas to the surface. We're losing some of the volatiles to the vacuum of space. So we know that that occurs because a lot of these lunar volcanic samples, so similar to what you might go out and pick up if you went to Hawaii, a lot of the samples that we have, these volcanic rocks, have lots of holes in them. And that indicates that as that rock was cooling, was water that was present in the melt was being lost. And so we can explain all these variations by modeling magmatic processes. What I want to draw your attention to, though, are these yellow circles. And so whilst the majority of volcanic rocks show this large spread, and we have to deconvolve all those processes that happen during eruption, pre-eruption, and also post-eruption, these values are really important. And so what these data points are showing you are the values from melt inclusions. Now, melt inclusions are pieces of magma that got trapped within a crystal very early on.
This is Kathy.
Oh, hello, Kathy.
Sorry, this is Pima County Office of Sustainability.
Oh, I think.
Kathy, can you mute your computer?
That doesn't
Okay.
sound familiar. Is he with the county?
Oh, I'm just going to fly on.
Hmm.
So these.
Yeah, I'm not in the attorney's office. But what I can do you have
Okay.
his number?
So these melt inclusions are trapped pieces of magma that were enclosed in a crystal very early on, before much crystallization of the melt. And so they really give us an understanding. Oh, okay. I'll answer that question at the end. I'll come back to that. So these can give us an idea of what the melt was like, both chemically and isotopically, before degassing, before volatile loss, before eruption, before even a lot of crystallization of that sample and cooling. And so they're really important for understanding what the interiors of planetary bodies are like. And a lot of people do work on melt inclusions on terrestrial samples to get an idea of what the mantle of Earth is like. So for the moon, these are really important. And these olivine hosted melt inclusions are inside olivine. The olivine is this darker gray around the outside, and they're trapped within these little glass beads. And so what these materials tell us is that the pre-eruptive magma had a isotopic composition of more positive than Earth, which is indicated by this dashed line, at around plus 2000 per mil. So more fractionated, heavier in the deuterium isotope than we see on Earth. Now that was, oh, I lost the ability to, there we go. And so that was all well and good, but what we wanted to do was assess, well, what ancient lunar water? Those volcanic glass beads are telling us what happened in the kind of 3 billion to 3.5 billion year time scale, but we wanted to learn what happened prior to that, what happened at the very earliest stages of the moon. And to do that, we used some of the rocks from the lunar crust. Some of these rocks have ages between about 4.4 billion years old and 3.9. And so they formed just after the end of magma ocean solidification, which is what I talked about at the beginning. And so the bottom line from analyzing these samples is that yes, there's a spread, but the majority of samples show limited range in their isotopic composition. And so we think that these rocks are recording the signature of lunar water very early on in the moon's history, potentially showing us what the fingerprint of water was in the Earth-Moon system right back when the moon formed. And so I'm just going to skip on. So this brings us on to the origin of lunar water, and coming back to this plot that I showed you right at the beginning. So not only from the samples can we assess the isotopic composition, we can also assess how water is distributed within the interior of the moon. But for now, I'm just going to focus on the heritage, so understanding where water may have come from. And so if we just look at those crustal samples and melt inclusions, which give very similar deuterium to hydrogen ratios, we see that they show this range, which I've indicated as being lunar interior. We see this range, which overlaps with Earth's mantle, it overlaps with Martian meteorites, and it overlaps with some carbonaceous chondrite materials. So materials like what we expect to get from the asteroid Bennu from the OSIRIS-REx mission. And so we postulated a few years ago now that water in the Earth and in the moon, ancient water, seems to be, yes, there's some uncertainty, but it seems to be fairly similar. And so the question is, well, when did water come to the moon? And in that case, when did it come to the Earth? And so we postulated two scenarios. So either volatiles like water were present in the proto-Earth before the giant impact event that formed the moon. And during this process, where you have the impact come in and from this material that kind of shot out, the moon forms, that water could survive this type of impact event. Or we posited that before you completely solidify the Earth and moon, they are seeded with impactors like carbonaceous chondrites or comets. It turns out comets are not a very good source. but they could have been delivered after the formation of the moon. And so we addressed a little bit, and I don't want to go through the plot in too much detail because I'm running out of time. But basically, from doing some modeling, comparing the hydrogen isotope compositions of meteorite samples that we think come from these carbonaceous chondrites like Bennu material, from remote observation of comets, from observations of the solar photosphere, and comparing those to what we measured in the lunar samples, we showed that if we go with the accretion idea, so this idea that we're accreting water to the Earth-Moon system late on, it's most consistent with accreting water-rich carbonaceous chondrites, like the material we're hoping to get from asteroid Bennu. And we showed that comets likely played a very small role, if any role, in delivering water to the moon and the Earth for that matter, because comets have such a different, if I just go back a couple of slides, comets have such a different hydrogen and nitrogen isotopic composition that we just can't, no mixing of a nebula, solar nebula value and cometry is going to give us the values that we need in the Earth-Moon system. And so the likeliest source of water is from carbonaceous chondrites if it was delivered late. Now, prior to all this new lunar water work getting started in 2008, there was a model that came out in 2007 that suggested that, you know, this is the proto-Earth and this is the proto-lunar disk, so the magma disk from which the moon is formed eventually, that during this time, water would have been lost from the disk. But that's before we knew that there was any water in the moon. So these models were all assuming that the moon was devoid of water and trying to explain that loss through their models. Once we detected water in samples, all the experimentalists and theorists had to go back and change their models and see if they would work with adding water into them. And so luckily for us, the new models indicate that having hydrogen species, whether that be hydrogen, molecular hydrogen, hydroxyl OH, or water, that they can be retained through this turbulent high energy phase of lunar history. But there are lots of open questions with regard to the origin of water on the moon. I just showed you two M-member scenarios, but really we don't know at what stage in lunar history water was either delivered or if it survived. And because there's this consistency between the water composition in the Earth's mantle with what we see in lunar rocks, it's hard to differentiate whether it was delayed and similar bodies were delivering that water, or whether it just survived and we end up with the same isotopic composition in both bodies. We don't know how heterogeneous lunar water is, whether there's a difference between the near side of the moon, so the part of the moon that always is facing us, and the far side, back side of the moon. We are still trying to understand how the evolutionary models, that magma ocean model, how that's affected by including water. And we don't know, as someone asked earlier, we don't know really the connection between water that we see in the interior, so what's recorded in rock samples and those glasses, with what we see on the surface by remote sensing. And so that's where the field is currently going, is to understand that relationship. And so I just wanted to end really quickly by talking about the new NASA project that we have. And so when was it? In 2018, NASA solicited proposals for what they called the Apollo Next Generation Sample Analysis Program. And the goal of that program was to maximize the science derived from samples returned by the Apollo program in preparation for future lunar missions that are anticipated in the mid-2020s and beyond. And what NASA did was they were willing to open several Apollo samples that had never been studied. So the Apollo astronauts brought back 382 kilograms of material. There was a subsection of samples that were selected to be put in storage, to be either specially curated in different conditions, or to just be locked away and not opened until a time when technology had increased and improved to the point where we can make new discoveries on those samples. And so they really kept those materials for generations, scientists like myself, who weren't around in the Apollo era. And those samples include an unopened core sample, unopened and vacuum sealed core samples, samples that have been stored frozen at -20°C for 45, 50 years, and samples in helium. And in March 2019, NASA selected 9 teams to do these investigations to open up some of these new samples. And we were lucky enough to be selected as one of those teams. And so as part of that selection, what NASA offered was, there are 9 individual teams, but several of the other teams wanted to open a core sample. And so NASA gave us the opportunity to collaborate with that core consortium and part of a larger ANGSA project as well. So we have our own project, which is this #1 that I'm going to talk about, looking at volatiles, looking at water in Apollo 17 basalts. But then we're also part of this big core consortium, which is a team of over 50 researchers from all across the world. Okay, and so just to show you the faces of the people involved in our consortium. So we're a group of 7 people from across the US, including my grad student, Zoe, who's at LPL. And together we are investigating 4 lunar samples, one of which has been frozen for 50 years. And so these together are called the Steno crater basalts. They're volcanic samples. And they were all chipped from this boulder on Apollo 17. So this is an Apollo 17 NASA image. This is the edge of the crater I've just outlined in yellow. And that's why all these refer to them as the Steno crater basalts. And they were each chipped off of this boulder. And the numbers, the 7 stands for Apollo 17, the 1 stands for Station 1, and these are the subsample numbers. And so we're looking at these 4 numbered samples that were chipped from this rock. And so this is a picture prior to that chipping. So we have 4 samples, 3 of which have stored at ambient conditions, so room temperature for 50 years in the NASA's curation facility, and 71036, which was collected over here, has been stored frozen for 50 years. And so the goal of studying all 4 samples is several. But before I do that, I want to just talk to you about what we're planning to do. So we want to understand minerals that are there, both 2 dimensions and in 3 dimensions. We want to understand the morphologies of these samples that have been, no, the frozen sample is never studied. The other samples have been, have had very little work on them, even if they've been available to the science community. So we really want to understand the mineralogy and petrology. Of course, we want to do volatile element analysis so we can understand the water contents and hydrogen isotope compositions. We also want to understand the age of the samples that have not previously been determined. So we want to understand when they were erupted and what's happened to them since they've been at the surface of the moon and look at their surface age. And so by comparing the water content and signature of water between the room temperature samples and the frozen sample, we'll be able to assess whether being stored frozen is a worthwhile thing to do for future return materials. So hopefully we'll be able to make some assessment as to whether NASA's been curating their samples appropriately. I mentioned earlier this idea of volatile loss from the volcanic samples, that when they're erupted, they lose volatile elements like carbon, they lose hydrogen. And so you have to tease out and work back, model that volatile loss. You just real quickly, if I go back, this is what I was talking about when I said we see from samples that they've lost volatiles. These holes that you see in these volcanic rocks indicate to us that as this rock was cooling, as it was erupted, it had gas bubbles, and those bubbles essentially popped and lost those volatiles to space. And And so we want to also tease out the signature and origin of lunar magmatic water from studying 4 samples in the most detail possible, and also determine the ages and whether they're from the same lava flow, which could give us a time sequence. If they're not, it could give us a time sequence. And so we've been unfortunately hampered by shutdowns and also by COVID, but we have been able to do some work. And so grad student Zoe Wilbur has been hard at work using some data collected at NASA's Johnson Space Center earlier this year. So she has, similar to the map I showed you earlier, this is a thin section map of one of the rocks, one of the room temperature rocks. And by using energy dispersive spectroscopy, she's been able to map the X-ray counts for different elements: iron, magnesium, silicon, aluminium, potassium, titanium, and phosphorus, color code those different maps that we get for the sample, combine them so that we can tell the mineralogy. And so each of these different minerals are indicated in the sample, and you can see it has a really nice texture to it. It's a volcanic sample. This is one of those vesicles, so evidence of volatile loss in the sample. And because of limited access to equipment, what Zoe's been doing is actually doing a really nice job of taking these types of maps, and by using a software called ImageJ, she's been looking at the modal abundances of these different minerals and comparing them to some very preliminary studies that were done in the 70s and one in the 1990s. And she shows that in 2 dimensions, she's getting very similar modal mineral counts for these samples compared to those previous studies. I wanted to show you a video. I hope this works. She's also been using microcomputed X-ray tomography to look at the 3D modal mineralogy of these samples and to look at the distribution and form of the vesicles, those void spaces in the samples. So hopefully this works. So this is a 3D rendering of one of the samples, one of the room temperature samples. The blue is the outline of the kind of a mask of the sample. And what you're seeing in yellow are the ilmenite crystals. So those are iron and titanium rich oxide minerals. And so this is just a movie. You can see that there are lots of void spaces all around the sample. I'll just play that again as I'm explaining their figure. And so what Zoe do is to give different minerals different colors and then do the similar thing to the 2D modal mineralogy, do it in 3D. And here she's compared one of the ambient samples, the 2D and the 3D mineral compositions to mineral modes to each other. She actually is showing that there's a difference. And that's important because we make a lot of inferences about the chemistry of moon rocks from 2-dimensional thin slices of the rocks, but actually they may not be representative of the entire sample that we have brought back from the moon. And so this is a new technology. This micro-computed X-ray tomography is a new technology that's only recently been applied to Apollo sample and is really providing us information. And she's also been looking at the spaces. So here you see kind of still of one of those movies, where here you're seeing in purple the combination of void spaces within the sample. So this is evidence that these samples lost volatile elements. They lost these really low temperature species to the vacuum of space. And actually, once they're lost, they can either be lost to space completely, or they rain down dense on the surfaces of minerals and rocks that are present surrounding that fissure, for example, where volcanic material erupted. And so I only have about 5 minutes left. So I just want to zoom on really quickly. That's as much progress as we've been able to make. Hopefully we'll be able to.
Questions. So I just wanted to make sure we had a little bit of time. Is there something you still really want to show us here? Just because we have a few questions in the chat. And
that's okay. We can just stop here. That's fine. I just wanted to show you some of the core consortium stuff, but I'll get too excited and go for too long. So we can just stop and go through some questions.
This has been totally fascinating. Wow. And those pictures of those rocks, really. Maybe since we're all spending more time on our computers, maybe we're paying attention to some of these things. Well, I wanted to make sure that we got to questions. We have a question from Leslie Watson, about sort of the big picture, the capture of this water. How does it help us understand Earth developments in history, I guess, with water?
So by understanding, so the moon gives us, as I mentioned, that earliest snapshot of kind of understand types of bodies that were impacting the Earth-Moon system very early on, after these two bodies formed and kind of were set in their ways. And so now that we know there's a common heritage of water in these two bodies, we can now start to interrogate, well, what were the actual asteroids? What were the actual sources of water to these bodies? And not just water, but what about organic material? So we are water rich in organics and water. And we think that these two things may have been delivered together. And so that's actually the impetus for going to asteroids like asteroid Bennu with the OSIRIS-REx mission, because Bennu is a very organic, rich, and rich body, and so may give us clues as to, the origins of life on Earth, or at least the origins of the seeds that have initiated or given the ingredients for life on Earth.
Okay, and I'm going to jump to question here from Michael Breska. Is there a larger conceptual or theoretical question that you think your colleagues should be asking but haven't yet asked?
Oh, that's interesting. So something that we haven't, okay, so something that's only recently come out. So I'm gonna kind of turn it a little bit. Something we hadn't, so I mentioned this connection between interior water and exterior or surface water, and we don't really know that connection. But it may be a little obvious now from my talk that, we're expecting a lot of these volcanic rocks to have lost water to the surroundings. And there was that question earlier about this. But with the sheer volume of water that these samples could have had, they could have lost a lot of water to space and actually could have formed atmospheres, temporary atmospheres at the surface of the moon that then, once those volatiles condense, could actually be responsible for a lot of the surface water that we see maybe in the polar regions. And so volcanic degassing hadn't really been considered as one of the primary sources of that surface water. It was for the long time considered to just be solar wind implantation and cosmic ray exposure, so exposure to the surface space environment. But actually, volcanic activity could have supplied a lot of that water. And so we're now at a point where we've identified water on the surface, we've identified it in samples, but we don't know how much is on the surface. And so this is the real driving force for sending robotic missions to the surface of the moon. And actually, I just wanted to mention, in case you're not aware, the Chinese Space Agency just landed on the moon this week and collected a new batch of lunar samples. And they lifted off from the surface yesterday. They're now in orbit, and they'll be coming back in a couple of weeks' time to Earth. So it's a very exciting time to be a lunar scientist, and hopefully NASA can use to support going back to the moon in their Artemis program and look at water ice on the surface near the poles.
That is amazing. Sounds like you're going to have a lot more to study as a result.
A lot more, yep.
Well, I'm wondering, we are, I think, right about at 10 o'clock. Maybe what we can do is kind of close the formal hour of the presentation. But Jessica, I don't know if you have a few more minutes. There's still—
I can stick around for a couple more minutes, yep.
Well, I'd just like to thank everybody for coming, and Jessica for a really fascinating dive into what we're seeing on, the headlines and trying to connect together what some of this research is doing. So
thank you very much. I really appreciate the opportunity to come speak to everybody and meet more people around campus, even if it's virtually.